Okay. Hello, everybody, and welcome to today's Austmine webinar, Unlocking AI-Driven Predictive Maintenance in Mining by Razor Labs. My name is Sam Sakasiris, and I'm the National Membership Team Leader here at Austmine. Before we begin, I would like to acknowledge that I'm hosting the webinar from the lands of the Whadjuk Noongar people. I also acknowledge the traditional custodians of the various lands on which we all work today and the Aboriginal and Torres Strait Islander people that may be attending this webinar. I'm joined today by two people from Razor Labs, Michael Zolotov, Co-founder and Chief Technology Officer, and Andrew Kaushal, Vice President Sales Australia. In this webinar, Michael and Andrew will deep dive into how AI sensor fusion is revolutionising predictive maintenance in mining, as well as showcasing real-life examples of Razor Labs installations around the globe. We will also learn how Razor Labs is helping operations worldwide minimise costly downtime and extend the lifespan of critical assets through cutting-edge AI technology. As we would like this to be an interactive discussion, please submit your questions as we go. At the end of the presentation, Michael and Andrew will respond accordingly. This is a great opportunity to receive expert insights on the topic covered. There is a Q&A button at the bottom of the screen to send through your questions at any time. You can also upvote on other audience questions that you most want answered. We will try to get to as many questions as we can in the time we have remaining. We are recording this webinar and we'll make it available to all attendees with a link to the Austmine YouTube channel in the coming days. So with that said, I'd like to now hand over to Andrew to commence the discussion.
Thank you very much, Sam. Welcome, everyone. I'm Andrew Kaushal, VP of Sales at Razor Labs. We are proud to be leaders in predictive maintenance, especially in the mining space. I have spent a big part of my career working with sites across Australia and Southeast Asia, from iron ore to coal and everything in between. Today, we are talking about a shift that's already transforming the mining industry, sensor fusion and AI. With me is our CTO and one of the key minds behind this tech, Michael. Michael is a serial entrepreneur. He led companies through acquisition and IPO, helped drive Razor Labs' global expansion, and an expert in radar tech, AI, and analytics. Michael holds an MSc degree specializing in deep learning for medical applications. Michael, great to have you.
Pleasure to be here, Andrew. Pleasure to be here, everyone. Thank you.
Thank you. So, Michael, let's start with our very simple, and I would like to understand what is AI sensor fusion and why does it matter? If you can go through on the slides.
Sure. So imagine like a doctor, right? A doctor uses multiple tests. You go to a doctor and they use MRI and they use CT, they use blood work and ultrasound. And all of these different sensors or different data sources are used together for their diagnosis. And we perform practically the same but for machines, integrating together a very wide variety, both of sensors. You can see it here, motor current and pressures and flows and vibration and oil and cameras, and other data sources like fluid analysis, oil and coolants and fuel. In mobile fleets, we're using tire information and dispatch data, and obviously maintenance records. There are two goals for this data fusion and sensor fusion. One is to achieve a full coverage of the failures in a machine. It's obvious that a single sensor cannot capture all the failures altogether. And the second of all is to achieve a deep diagnosis, meaning not to say I have here a temperature above 80 degrees, but to achieve a deep diagnosis, having understanding the failure mode exactly, the root cause analysis of that failure, because if we deal with this one, it will prevent it from happening in the future and its exact location. Going just by a few examples, you will understand that pump performance can only be done with pressures and flows. Auto-spec ore will require a camera for this one. Oil leaks, obviously an oil sensor, and so on and so on. And we haven't even going to discuss the mobile fleet, which we're going to use. We're going to leave for a different webinar.
So what I'm understanding, it's more than just data, it's inside. Can you give a little bit more concrete real-world example?
Sure. So we can give an example of a mill to start with. The mill is obviously critical in many operations from gold to copper and other precious metals. And going through this one, you can see here one of the screens of the system where you know that the mill is such a huge machine that when you're in a long shot, you need to slowly rotate the machine. So you can see here one of the severity scores that the system is giving specifically to the motor of the mill. You can see here the different components. And you can see here that after a while, they had a long shot on site. It's been a month and a half of a shot. And unfortunately, during this shot, they actually forgot to rotate the mill. And the weight of the mill actually caused damage to the bearings. And when they were actually, these black dots are when the mill was down. And when it actually went back into operation, you can see that it already started orange, quickly deteriorating to red. Okay, so the team had real-time indication that something is wrong right after the shot, and it's actually deteriorating. Now, it's actually not a black box. It's not only saying the exact diagnosis of the drive and bearing deterioration, as you can see here with the causes and the action, but it's actually showing the reliability team on site what is the evidence. So it actually shows that within 1 week, roughly a year ago, they had in 1 week a deterioration of a 40 time in a specific frequency. And this is a very apparent deterioration in a specific frequency that indicates specifically the outer race deterioration of that bearing. And basically, the team on site, understanding that this is a very large machine, wanted to be sure, and they actually sent their own team, obviously, doing regular vibration analysis. And this is the signal that their own team got. And you can see immediately the difference between our signal, which is the fusion of vibration and motor current and tachometer and other sensors, and just a regular single sensor vibration in this case. When you try to compare the blue to the red, you try to understand, did it deteriorate? These are two also 1 week apart. You don't see here any deterioration, right? Sometimes the blue is higher, sometimes the red is higher. You don't see here any deterioration. Obviously, not clear as this super clear one when you're actually fusing together sensors, right? So here we fused vibration sensors together with the motor current, together with the tachometer, all together with sophisticated algorithms that we're going to discuss. And basically, they didn't see anything with a single sensor of a vibration sensor. And they basically took our word for it. They they basically had a shot 2 weeks afterwards. They reshuffled the tasks in order to take care of the mill to actually replace the motor. And when they actually took apart their old motor, and they took apart the bearing, they've seen this severe damage in the bearing that would otherwise would have cost at least a day of a shot, probably a few days. So we're thinking here of at least 24 hours of avoided unplanned downtime. Obviously, a mill has no redundancy on these kind of sites.
Exactly, and it builds trust. So when site sees this kind of foresight, adoption is much easier. It's just not like a cool alert. It's a serious business value. So could you tell me what did that save to the site?
So obviously, from our estimations and the site's estimations, it would be at least $500,000. It's a huge machine. You actually need to bring a crane in the middle of the night, pay after hours. The failure there actually would have happened around Christmas, so really a nightmare. Both looking at potential lost throughput, right? Because that part of the line would be down again for at least a day, probably a few days, but also increased maintenance costs, increased labor, and obviously overtime of the contractors. And imagine this is one mill, one failure in a single site. Now imagine when you multiply this one by many failures across a fleet of machines and across a group of sites. The potential here is really enormous.
Wow. Let's switch to coal because this isn't just about hard rock. So if you can like a little bit go through on the coal side as well and talk about that.
Sure. So we can basically take the example of a centrifuge in a CHPP plant in Queensland. And basically, you can see here how our nominal deployment looks like. We are always reusing existing sensors on the machine. So in this case, they had a motor current and a tachometer on the machine. But this machine actually lacked vibration sensors that we added as a part of the implementation on critical bearings in the machine itself. And it's obviously its drivetrain, like the motor and so on. And one of the key facts about a centrifuge is that after you perform maintenance to it, after it has been down, it's critical to basically clean it from debris and basically a residue that can settle on the walls of the drum of the centrifuge. And basically, in this case, they skipped the cleaning, and you can see already that after the maintenance was done, they went immediately to alarm because that debris and residue basically made the machine highly imbalanced. The drum itself was highly imbalanced, and you can see here the diagnosis that includes basically it says imbalance as a failure mode. There is a deep root cause analysis showing exactly what are the causes potentially for such a machine and such a signal and so on, and what actions are recommended. And within the planning section, they can actually see what is the proposed work order that can automatically, the notification can be automatically generated based on this condition. And basically looking on the data from a time series perspective, you can really see the normal operation here. That's all a screenshot from within the system. And right after the maintenance, you can see a spike, right? The entire baseline of the vibration became dramatically higher by at least 2-3 times. And what is amazing to see here is that from that point, they knew about it literally that day with other systems or with vibration analysts that have been, checking on site for every 6 or 8 weeks. It would take a much longer period of time. The issue was here actually resolved within literally 2 days. So you can see how already in January 29th, it was completely resolved. From a spectral perspective, we're using here the vibration to exactly identify the failure mode itself and verify already after the cleaning that it went back to normal operations. And indeed, within the dashboard, after the normal operation, it went to orange after the initial bad maintenance. And after they fix it, again, real-time indication that they're now back to normal, also giving them a measure of the efficiency of itself of the maintenance. And again, what is amazing to see here is that an issue that could have been overlooked for months and even more had been resolved within 2 days. So an online system that has been using the various sensors here of the centrifuge just gave them the heads up right on that same day. They reshuffled the tasks that they had in the downtime 2 days from that point and went back to green. And by the way, here it's not only shortening or the potential shortening of the life of the centrifuge that did not happen because it was resolved pretty quickly. But this residue actually reduces the efficiency of the centrifuge. It actually reduces its effectiveness. And again, here instead of lasting for months or whatnot, it was resolved by in 2 days.
Nice. So what I'm understanding, it's just not machine diagnosis, but also identifying poor maintenance and giving site leadership better control. Plus, machine life get extended, meaning lower maintenance cost and fewer components replacements on site. Nice. So if I go over now changing the script and everyone is talking about AI, let's talk about AI itself. Everyone says we are doing it, but few actually are. So can you take through what's the differentiator over here is?
Sure, fantastic. So let's speak about the AI under the hood here and actually how it works. So first of all, a major differentiation is that traditional AI or older AI, as you know, requires tens of thousands or even hundreds of thousands of examples of failures or whatever you're trying to teach it. And we see systems coming to site and requesting the site to actually train the system, calibrate the system for a prolonged period of time, of at least half a year, even a year and more, because their traditional AI is actually learning by these examples, and it puts huge burden on the teams that are already overworked on site to also start training their AI systems. We don't think that it really fits the mining industry, so we've built here a very different approach of training these models. And the key differentiation here is that this AI is pre-trained. All the knowledge that's required for the diagnosis of the failure modes, of the root causes, of what are the actions, it all comes pre-built into the AI. And after all the sensors are there, literally in a few days, it's up and running. If any sensors are missing, literally after we walk out of the site, deploying the gaps of the sensors, again, in a few days, the system is up and running, and it does not require the site team any training or any teaching. The way that the AI work, and we're going to go now from left to right, is first of all, the AI is looking at a very diverse set of data points. We have vibration data, which is actually spectral data. We have camera footage, which are raw pixels. We're going to give a few examples in the next few minutes. We have other telemetry like pressures and temperatures and currents, and they are all different from one another, but they all need to be analyzed together. First of all, we have a set of models that analyzes each of these data sources to extract critical features, and then they go into a large neural network that is trained by a very unique way called semi-supervision. Semi-supervision is very similar to how ChatGPT is trained, and as you know, when you log into ChatGPT, you can start just using it. You do not need to teach it or to train it, and you can just use it out of the box. We've used the same method for our AI. And the output of this huge model is, there are several heads or several outputs. One is the location of the failure. We put here an example on the right side of how it actually looks like in the system. So it can be specifically the drive and bearing of the motor of that specific compressor. How severe it is, right? Is it something that can wait for the next shot, or is it something that's requiring the attention? It's worth noting here that we're giving a heads up in most cases of at least a month, and if not several months up until failure happens. So you have plenty of time to reshuffle the tasks of the next downtime in order to obviously perform these actions. What is the exact failure mode? So I put here an example of lubrication issues, but it can be gear mesh issues, oil leaks, material issues, and so on. We're gonna see a few examples. But also importantly, what is the root cause? Like you've seen here, right? The imbalance is caused because of debris, and what are the recommended actions for them to perform in order to obviously resolve the issue? And the critical part here is that it's not some symptom of you have a high temperature here or low pressure there, which is not actionable, but it's really precise root cause that tells you exactly what needs to be done in order to resolve it.
Cool. Now that's like a very big advantage, and removing the night for the long on-site training phases. And the other biggest thing is that what I'm hearing it is that the system is ready to go from the day one and without slowing down the site team. That's fantastic. And in terms of the AI training method, sounds like a smart way to overcome the data gaps and most other vendors struggles with. That's how I'm reading it. Is that correct?
That's correct. Sites don't have hundreds of thousands of examples of failures. Actually, each of these failures on their own, I don't think that in the entire history of humankind, you had 100,000 or hundreds of thousands of examples of, for example, debris in a centrifuge.
Cool. So let's level up. Visual AI. What can deep learning actually do in a mine?
Fantastic. So it's a very good question. And I think that what's very unique about cameras is that there might be the only sensor that actually allow us to look at the material itself. So one use case is conveyors. We can go from left to right here, but for example, looking at out of spec ore, this is critical to diagnose crusher liner wear or miscalibrated crusher gap. Belt misalignment, you can see here that we're measuring the distance from the tips of the belt to the tips of the rollers to make sure that the belt is aligned. Misaligned belt can go unnoticed for months. It's actually reducing the life of the belt, increasing the amount of belt replacements that are done, and also reduces the life of the pulleys of the belt. Variations of volume, which are very important for before grinding circuits, right, in the feed to mills, for example, because they make the grinding less efficient. Blockages and rips of the belt, as you can see here on the left side. And basically what the deep learning does is it takes raw pixels, a bit like we've seen in the previous slide, and out of these raw pixels, it measures specific parameters. So for example, if we're looking at oversize, it's measuring every rock. It knows what should be the crusher gap, and it's trending the oversize, right? So basically the deep learning, the AI models convert the raw pixels, clear operational metrics, alignment of the belts, oversized. And once these are trended, you can basically start setting alarms based on them. So you can see here how in one of the sites, every time they have an increase of the oversize, they know that their crusher liners are worn out, and they're basically just go ahead and proactively fix the issues. Before we install the system, it actually caused them downtime in their mill. So the mill was getting oversized and it was actually tripping on overload. Since we installed the system a few years ago, they just didn't have it since. Same also goes for flotation cells. I'm not sure that you're seeing the video here, but basically measuring the size of the bubbles, the velocity and density of the bubbles, which give a real-time indication of the efficiency of recovery, whether it's in gold sites or other precious metals.
Cool. So I imagine this adds like a whole new layer of visibility, especially for like a process-related faults. And this like adds a great point. For most sensors don't capture what's actually happening with the material. So it's like having 1,000 set of eyes 24/7.
Correct.
Cool. So if I go to the next is in covering more on the machine sides and what are the equipments are actually covered and what's in the scope on the fixed asset side of things.
Sure. So taking just some of the major examples, we support basically all fixed assets, really from reclaimers and stackers and ship loaders to crushers in the crushing circuit, from jaw crushers to cone and gyro crushers, ball mills, sag mills, AG mills, rotation cells like we've seen, obviously all conveyors, both in booms of the material handling, but also yard conveyors and so on. Centrifuges that we've seen, tons of fans, ID fans, FD fans, sinter fans, which are common in smelters. It's not only mines, it's obviously also wash plants and processing plants, smelting facilities, refineries, pumps and compressors, obviously. We are also covering mobile fleet, but it's a subject for a different webinar.
Totally understand that. Just to understand this a little bit more, and what about the integration to work order systems already in place like SAP? How do we leverage the existing systems of the mining sites?
That's it. So it's a very good question. And basically, we integrate both to SAP or other ERP systems for two main purposes. One is to get work orders and understand what maintenance is done on site. And the other one is to create automatically maintenance notifications based on what is right now deteriorating. It's basically closing the loop from monitoring the equipment to making sure that the actions are really happening. We've been partners of SAP for the past 3 years. Basically, when a work order is received, what the system does, and I've given here a real example of one of the compressors that we're monitoring in Fall site in New South Wales. And basically, what happened here is that you're seeing that they're performed lubrication. The way that we know that they performed lubrication is that we integrated to SAP and got the work orders. But we can see that after the lubrication, not only it was not effective, but it actually became worse. So the system itself is actually taking the work orders and correlates them with the health of the machine. And it anticipates to see, obviously, improvement in the health. If it's not happening, then we can take it a step forward and proactively inform the site that this maintenance was not done effectively. In this case, by the way, according to the OEM instructions, they needed to lubricate between 30 and 40 grams of grease, and they actually only put 10. And the only way to know about it is to integrate to SAP, to get a work order, understand that the team on site performed maintenance, to see that it was not effective because the AI sensor fusion is diagnosing the equipment. It's actually seeing it not improving because of the maintenance. And obviously then the team on site can be instructed to, in this case, put the proper amount of the lubrication.
So this actually closes the loop between the machine conditional monitoring and the creation of the work order to fix it. And then the system checks if the maintenance action was successful, making sure the issues was really resolved. Is that correct?
Exactly.
Cool. Michael, as we know that mining isn't a Silicon Valley. So there are the tough environments. How do we make the implementation work? Can you talk about that?
Sure. So we really built a clear methodology on how to do it. We really keep it simple and short. First of all, we actually come to site for a site survey where we map the critical equipment. We map what is the single line of failure that when some machine stops along this line, this entire line stops. And we basically choose the critical equipment. It can be the crushers, the conveyors, it can be some critical part that is in charge for a main line of slurry and so on. And we basically we send our local teams. We have local teams obviously in Australia that come to site and choose together with the client these critical machines. They also see what sensors are available because, as I said, any sensor that's available, that's relevant for diagnosis, we use these sensors. We have a clear methodology where we know what sensor is required and in what location, and obviously for what purpose. And in any place where sensors are missing, we're basically building a very clear implementation plan saying what sensors will be added in what exact locations down to their exact orientation on site on the machine, because different failure modes will result in this case, an example of vibration of different axes. So the team on site has a very clear understanding of where new sensors will be deployed. And again, once the sensors are deployed, we basically walk out of the site and the system is up and running. It's getting all the data, both from our sensors and the existing sensors on site, analyze this one, and basically gives a diagnosis 24/7 for all of the machines that are monitored on site. And basically, obviously, our local Australian teams are providing ongoing support for the site with any questions that they have.
Fantastic. Michael, I have traveled to a number of sites here across Australia, and one of the most common questions I hear, what makes Razor Lab different from every other conditional monitoring tool? I'd like to hear your thoughts.
Sure. So basically, our differentiation is that when you look at other tools, they mostly offer dashboards with tons of graphs, tons of raw data that the sites need to analyze by themselves. Here, basically, what we provide is kind of a set of automated doctors looking at your equipment 24/7, not missing any failures. That's what the AI sensor fusion, which is very unique here, is delivering. Now, instead of giving some vague alert like your temperature here is above 80 degrees and thousands and thousands of false alarms like any user of SCADA knows about it, we're telling you exactly what is the failure mode, what is the root cause, and what needs to be done. And in order to do it, under the hood, we actually use sensors that others don't use, like the cameras, like unique oil sensors that give you minute-by-minute oil readings, unlike laboratory tests, which are only once every month or every 6 to 8 weeks. So the sensor fusion, both from the hardware part and the diagnostics part, is very unique. Training methods that we've put here are very unique to, as I said, prevent the site team from needing to train the system and teach the system. It's not required here at all. And we've actually built some sophisticated techniques because mining machines are so noisy, right? They're grinding, they're crushing, and this noise is actually much higher than the noise of the failures, right? A bearing like that produces dramatically less noise than a huge mill. And we've built algorithms like envelope demodulation and other vibration analysis processing algorithms, basically cut through the noise, reduce it dramatically, and be able to see failures. So it actually allows us to see failures that other systems cannot detect, like the ball mill example that we've given, where a regular vibration reading was just too noisy. You couldn't see the failure there, but our system was able to pick it up very clearly. We deploy any sensors that are required. So if the sites are missing some of the sensors or even all the sensors, no worries. We got that one covered. The system comes pre-trained with all the knowledge. We walk out to the site and it's just up and running and just works. So it's really built for operations, not for data scientists.
Fantastic, Michael. This has been brilliant. Any final thoughts?
So I guess that I would say that mine sites are used to very painful, long AI rollouts. And with traditional AI, it was actually true, needing to train it and to teach it in parallel to your actual job in the mine site. As I said, our AI is trained like ChatGPT. You don't need to train it. You just use it. Typically, a deployment just takes a few weeks by deploying some relevant sensors that are missing. And basically, what the site gets is like a 24/7 copilot that just helps you prevent unplanned breakdowns, giving you early notice of at least a month, in most cases, several months. And I guess it's not some theoretical concept, but it's really a proven system that has been deployed in Australia and South Africa and Latin America for the past years. And the goal is, number one, obviously, to reduce cost of maintenance, because if you find an issue early, the maintenance would be dramatically lower in costs. If you turn unplanned to planned, the cost would be, in most cases, 3 to 5 times lower. Increase the productivity, but also make the site a much safer place by not putting personnel next to equipment that is failing many times in dramatic breakdown ways. And we basically allow the site to focus on the real work instead of constantly firefighting for breakdowns of equipment.
100% agree. Could not have said it better. Thank you, Michael. And I'd like to say thank you for everyone and for tuning in. And more episodes will come soon. I'll open the floor for the questions.
Thank you, Andrew. It's been really a pleasure. Looking forward to getting your questions, guys.
Yeah, thank you, Andrew and Michael, for that very insightful presentation about the fantastic platforms and products that Razor Labs have. I do have some questions from the audience, so I'll go straight into them. The first one is, can you add a cost factor to the maintenance required? For example, replacing an item prior to breakdown will cost X, but a failure breakdown will cost X plus Y. Therefore, you can decide if the extra cost is worth the risk of working the machine to failure.
Sure, it's a very good question. I would basically break down the answer to two options. We mostly ask the site, are you mine constrained or plant constrained? If you're mine constrained, you will be mostly looking at reducing the maintenance costs. And in this case, from our experience and working on business cases with customers, typically planned maintenance would cost 3 to 5 times less because number one, spare parts are much cheaper. It's much cheaper to lubricate a machine and it takes 15 minutes and not to replace the machine when it's already critical. So actually picking up on these failures earlier has a major cost benefit. If you're plant constrained, obviously in most cases, you will be looking at more productivity, and then you will be asking yourself, okay, this machine is a part of the line. When this line stops, because this machine stops, how much am I losing? How much am I losing? And then you will probably be looking at how much is your throughput worth in terms of 1 hour. So you multiply your tons per hour by the amount of dollars per ton. So it really changes from one side to another, and mostly we're using several KPIs. It's not a single KPI to put all of them together, and obviously the site puts the final numbers.
Thank you, Michael. The next question is, does the system identify incorrect data being used by a broken or out of spec sensor?
Sure, it's a critical part. The answer is yes. Not only in simpler sensors like temperature, where you just go out of physical boundaries, or when your motor current is negative, that's easy. But also for vibration sensors, so we can actually pick up patterns within the sensors that allow us to see that this sensor is loose or this sensor fell completely, amongst others, by both looking at the patterns in the vibration itself and comparing different sensors that are on the same machine.
Thank you. The next question is, do I have to use your interface? Can I get the data out so I can use it on another platform?
So the answer is yes, you can get the data out. You can get the data out both in terms of the bottom line diagnosis. So as I said, what was the urgency, the failure mode, root cause, and so on. You can actually integrate it into your APM system and look at everything there. And also look at the raw data itself. So you can get the raw data. We partner with other companies like Aviva and others. You can look at the data in your PI system and others. So no, you don't need to look at our interface. And I would also say that when we see deterioration, in most cases, we have integrations to SMS messages or emails and work and maintenance notifications that you would get. So you do not need to continuously refresh the dashboard. You will get an alert from many different options that exist.
Thank you. Our next question is, how does the system handle equipment with variable speeds or intermittent operation?
Okay, it's a fantastic question. The problem with these machines is that if a machine is right now working harder or rotating faster, you will obviously have higher vibration as an example. In many cases, also higher temperature in others because the machine is under higher load. Systems that don't compensate for this one will just have false alarms. Every time the machine will work harder, vibrations will go up, it will cross the threshold, and you will get false alarms. What our system does is the model looks at the relationship between how hard the machine is working. We get this one from motor current and tachometer, so how fast it's rotating and under what load it is. And it's actually able to compensate for that. So it will anticipate higher vibration and higher temperatures and so on in these conditions. And because it compensates for this one, the thresholds will actually be dynamic and adjust these ones. So it takes this one into account. That's why the motor current and the tachometer and cameras that look at the amount of ore that, for example, go in the mill are so important, because they're giving us the understanding of the instantaneous load of the machine.
Thank you, Michael. Our next question, do the sensors need to be continuously connected to Wi-Fi?
So the sensors are wired, they're not wireless. The reason for that, so it means that they are wired into our gateway. The gateway has SIM card, not Wi-Fi in most cases, SIM card that sends the data to the cloud. The reason why it's so important, and we do see other sites sometimes using wireless technology, is that by definition, the higher the weight of the sensor or the heavier the sensor, the less accurate and the less sensitive it is. That's just the physics of it. And when we look at the wireless sensor, it's much heavier because most of the weight is battery. So in critical equipment like crushers, mills, conveyors, and so on, actually putting a wireless sensor will mean that you have a much lower frequency range that you're able to monitor, that you're able to see, and higher frequencies where all the friction, lubrication issues, and so on, in most cases, will just not be detectable. So we'll be actually missing failures. That's why our sensors, in most cases, are wired. Only in very specific special cases we'll put wireless sensors. These are wired sensors. They connect to a gateway, has a SIM card, and the data is sent to the cloud for analysis.
Thank you. And just on the topic of the sensors, how do you decide where to place them?
So it's a very good question. We have a methodology. So in these last 10 years of R&D, we've mapped exactly what are the machines, their components, their failures, and their root causes. So we kind of have like a full FAMICA table. And because we know what failures different machines can experience, we know what sensors are required. So we know that we need to put motor current sensors here and tachometers there. We know exactly at what orientation put vibration sensors. We do not put all three dimensions, vertical, horizontal, and axial on every bearing because it's just too expensive. So we have an exact methodology of how to do it. We know where to place cameras, oil sensors, and so on. It's just a methodology that we've built over the years.
Thank you. Next question. How does AI sensor fusion improve failure detection accuracy compared to single sensor systems?
So good question. First and foremost, when you have a single sensor, you're not able to detect all failures. If you have vibration, you will not be able to look at the pump curve. If you have oil, you will not be able to see material. So by definition, all of these sensors are required to just capture all the failures that can happen to equipment. We see many sites that just go ahead and deploy single sensor, single type of sensor everywhere, but they will still experience breakdowns because these sensors will be limited to whatever they can cover. And the ability to also put all of these sensors together allows us to also deeply understand what is the root cause, so we can also prescribe actions and not just tell the site you have high temperature here, go and investigate, and practically we want to reduce their workload and not increase it.
Thank you. Next question. Can the system integrate with the site's existing condition monitoring tools or historical systems?
For sure. If the site has existing condition monitoring systems or sensors, and they allow us via API or any integration to get the data, for sure, we see sites where the vast majority of sensors are just their own sensors. For us, it's ideal. We would love to come to a site, have no sensors to deploy. We're essentially a software company. That's what we would love. We only deploy sensors wherever there are gaps, where they don't exist. Any condition monitoring systems or sensors that exist, we'll be happy to integrate to them. And obviously, historians, SCADAs, and other OPC servers, anything that the site has that allows us to get the data.
Thank you. How does the platform differentiate between process-induced anomalies and actual equipment faults?
So because we're able to see the material itself via the cameras, and because we know what is the load that the system itself that the machine is experiencing, we're able to differentiate, is there something different in the process, or do we see that the process is the same and the machine is deteriorating? Because we're using here with the sensor fusion all the process parameters, the system in its models can actually see, is there something different in the process? For example, there's a high load, or the material is different. It would be a completely other different root cause. We would call it an external root cause than an internal one, where the process is basically very similar, even the same, and we still see the machine deteriorating.
Thank you very much, Michael. Let me just see if there's any more questions coming through.
I would even go, according to the last question, an extra mile and say that in mobile fleet, we can even see when the operator is actually abusing the machine. So in fixed assets, obviously less relevant, but in mobile fleets, when they're actually physically driven, we can even spot these abuse of transmission or final drive and so on.
We've got a couple of questions about cost of the sensors, including installation and the cost of the system. Did you want to cover that now?
Sure. I can speak about the cost model. Basically, aside from the hardware, which is a one-time cost, and the implementation, just like any other system, where basically our pricing model is a subscription according to how many data points are being analyzed. So obviously, the more data points, the higher the subscription. We have 3 packages, and we'll be happy to take it basically offline to a more detailed discussion.
Exactly.
Thank you. Doesn't seem to be any more questions coming through. Oh, hang on a minute. Let me just refresh. Can the AI or software generate the maintenance task when found the problem?
Yes, so it's very important closing the loop. Once the system sees that the machine is deteriorating, there is a maintenance planning section where they can actually, so it actually will create a maintenance notification, and the user itself can actually see what work orders they already have in order to avoid duplication. So they can also move existing ones and make them earlier if the machine is right now deteriorating. So it's both creating automatically maintenance notifications, but also giving full control of the timing itself. This is via the integration to SAP, via their SDK.
Okay. That looks like all the questions have been answered now. Look, thank you for the extremely valuable insights there and the questions from the audience. If we haven't gotten to your question or you think of one later, please send it through and we will get it to the gentleman at Razor Labs for a response. I'd like to give a big thank you to you, Andrew and Michael, for your time today. Your insights are appreciated as always. Just a reminder, we have recorded the presentation today and we'll send you a link to access the video through the Austmine YouTube channel. Thank you to everybody who's attended, and we look forward to welcoming you to the next Austmine webinar.
Thank you very much, Sam. Thank you to everyone for joining in the webinar today.
Thank you, everyone. Thank you.